see it now probably. Okay, so this is my second topic of presentation, contact lens assisted cross-linking for thin corneas. And I must say at the beginning that I do not have any financial interest in this topic of presentation. This is CACXL, that's the acronym that I chose for this, contact lens assisted CXL basically. And this is just a question for the audience, maybe, how much of minimum corneal stromal thickness do you need to do conventional cross-linking? And I'll just give the answer also. It is 400 microns. So you need 400 microns of stroma to be able to do conventional cross-linking, and this 400 microns that's often given as a value is not inclusive of epithelium, but it's exclusive of epithelium. So if you're looking at a topography map or something, it's not 400 microns you're looking for, but more than that, because if your minimum corneal thickness is, let's say, 420, your stromal thickness is possibly likely to be less than 400, and even a patient with 420 microns is a candidate for CACXL and not CXL. And in our hospital, we generally keep 450 as the cutoff. So below 450 with epithelium on the topographic map is where we go for CACXL, and above that we do CXL. Of course, sometimes just small variations like 450, 445, 440. We just go ahead with CXL also, but generally remember that the 400 microns refers to stroma alone and not with epithelium. So now, just to understand the problem of thin corneas, just play this short video. So let me just pause this here, sorry. So what we need to know is that there have been a lot of studies done. Walensacks, Pearl, all of these people have done so much studies on cross-linking, and what they found is that the cytotoxic threshold of ultraviolet A for porcine endothelial cell cultures is, the threshold is actually 4 milliwatts per centimeter square. And what riboflavin does is, so you actually need about up to 4 milliwatts to cause any damage. But riboflavin, which we put in for cross-linking to be able to create those cross-links, it's actually a double-edged sword. It helps you as well as causes problems, because what it does is it induces UV toxicity at a much lower threshold. So it's the toxicity when you also add riboflavin to UVA happens at 0.35 milliwatts per centimeter square and not at 4 milliwatts per centimeter square. So, but riboflavin, as I said, also helps you a lot because it, sorry about that. It also acts as a sink. It acts as a sink and it absorbs the ultraviolet light as well, in which that's the way it helps you by decreasing the passage of ultraviolet light to the endothelium. So it absorbs a lot of the ultraviolet light right there in the corneal stroma. And that's the reason I said that 400 microns is important, because riboflavin saturated stroma of 400 microns is what brings down the ultraviolet light to a safe level at the level of the endothelium. So if you start off with 100% UV here, to bring it down to 6%, you need about 400 microns of riboflavin saturated stroma. And that brings it down to about 0.18, which is below the toxic level. And you can see this example when it goes to about 300 microns. I'm sorry. If for an example, if you're taking at 300 microns, what happens is your toxic level increases, because then the endothelium is closer to the UVA, and you get a higher level of UV reaching the endothelium, and that can cause toxicity. So basically that's about riboflavin and the stromal thickness and ultraviolet light. So again, this is the image which is very familiar to most of us. 300 microns of stroma and you get more UV, and that can be endothelial toxic. 400 microns here, as you see here, is a safe level of UV for the endothelium. And we all know endothelium is the most precious part of the cornea. And here what I did, this, we were doing hypertonic cross-linking and we were not very happy with it. This was way back in 2012, because we were getting scarring and haze post-operatively. And when we got the scarring, especially we know the post-CXL scarring that happens can cause a lot of flattening in that area, and very irregular corneas, which are very difficult to correct. So I was thinking in terms of what else we can do, and this is the idea that struck me, that what you need is riboflavin basically to attenuate the UV. So if the corneal stroma is not sufficient to attenuate it to a safer level, could you not just add riboflavin in some other form? And the answer to me was to saturate a contact lens with riboflavin, place the contact lens over the cornea, soft contact lens, because it would mold to the shape of the cornea, and that would start the attenuation at a level higher than the corneal stroma. So by the time it reaches the corneal stroma, it's already been attenuated to some level, and by the time it reaches the endothelium, it's come back to safe levels. So what the contact lens does is, it's a riboflavin saturated contact lens, and what it does is it basically attenuates the ultraviolet light, making it reach safe levels. And of course, the most important thing is that it should be, okay, I'll come to that slide later. The contact lens, what it does is it prevents ultraviolet light endothelial cell damage and also prevents the stromal haze that can happen otherwise. So this is a question that's most important. Which contact lens may be used? You cannot use any contact lens that comes off the shelf. It's very, very important. It's crucial, and this is important for the success of your procedure, that it should not have an inbuilt UV filter, because many of the contact lenses that are available commercially have inbuilt UV filters in them, and if you use any of those, obviously you would not have done any cross-linking for the patient at all. So make sure there's no filter. Check the product literature for that. You can just put the the contact lens under a UV filter and a UV digital meter and see how much is passing through, and that will let you know if you can use that particular contact lens. Thin lens design is important because you don't want to increase it by too much. The one that we use is 90 microns thickness. As I said, soft lenses follow the shape of the cornea, and we use hydrophilic lenses obviously because it absorbs the riboflavin solution. The one that we use in our hospital is a Bausch & Lomb soft lens, daily disposable, made of Filacilcon beads. Very, very easily available. It's extremely economic. I think one box comes to about $50 or something, and we can use it for so many patients, and it's a very safe technique to do. Here's an experiment where I took this contact lens, placed it on filter paper, and put riboflavin solution onto the contact lens, the contact lens that's held facing up. And when we removed it after different periods of time, we saw that the riboflavin has stained the filter paper underneath the contact lens, which obviously shows that the riboflavin penetrates into the substance of the contact lens and through it. It's not just a coating, therefore, it's actually saturating this contact lens material. Now, we did this is a paper by another group who showed that it's not just this contact lens, but there are other contact lenses which could be used for this technique. The technique is very simple. We remove the epithelium, and then we, at the same time that the cornea is being soaked in riboflavin, we also soak a UV barrier-free contact lens for half an hour. And then, of course, you're saturating both the cornea and the contact lens with the riboflavin. Then you place the riboflavin over the cornea, and you put this riboflavin film and then apply UVA. Now, that film is something that we should talk about again. In fact, some of my older videos on YouTube may show a subcontact lens film also, but we've learned with time that that subcontact lens film can cause too much attenuation of the UV. So we have had a lot of papers published on this technique now in JRS. This is we found this was our first paper. We found that we got an additional average of 107 microns using the contact lens. So corneas thinner than 400 microns we could treat. This is actually the flowchart that we use. We look at the epithelial thickness. Post removal of epithelium, we look at the stromal thickness, measure the pachymetry. If it is more than 400 microns, we do a conventional cross-linking or a conventional accelerated cross-linking. If it's less than 400 microns, then we put the contact lens also in for soaking with riboflavin. After half an hour, we look at the pachymetry again, and that's especially crucial if you're using riboflavin that is in dextran, because dextran can dehydrate the cornea. Now, if the functional pachymetry after half an hour is more than 400 microns, then you go ahead with contact lens assisted cross-linking. If it is less than 400 microns, now when I say functional pachymetry, please remember that this is the pachymetry of the stroma plus the pachymetry, additional pachymetry that the contact lens gives. So the patient stroma plus the contact lens, if it is more than 400 microns, then you can do CACXL. And a simple mathematics that I use for this is just take the contact lens to give you approximately 100 microns. So if you've got about 300 microns of stroma, just mentally calculate that the contact lens is going to give you an additional 100. 300 plus 100 is 400, and you can do CACXL. But if it's less than 300, then the contact lens is going to give you only 100. So you're still below 400, in which case, again, the cross-linking may cause problems. In this case, what I do is I put a couple of drops, just 2 drops of distilled water onto the cornea, and that gives you that very small amount of swelling. Generally, you need only maybe 20 microns of swelling that to take the functional pachymetry with the contact lens over 400 microns, and then you can proceed with the technique. We found that we got about 60 to 70% of transmission of the UV through the contact lens. That's what we got with the digital meter. And these are our techniques. These are our post-operative images. You can see CACXL with the demarcation line, a good demarcation line, as you can see here. No haze, good corneas. And this is with the accelerated CACXL technique. That's the technique we've been using now for many years, the ACACXL technique. And the one that we prefer is 10 milliwatts per centimeter square for 9 minutes, which gives a total energy of 5.4 joules per centimeter square. This is again an example of the demarcation line that we've got post ACACXL. We did this study with Cosimo Mazzotta, who's again another very well-known person in the field of cross-linking, and from Siena Center, Italy. And we found that post CACXL, the way the cornea would recover was exactly the same as a post cross-linking, conventional cross-linking technique. We found that there was no significant endothelial loss, pleomorphism, or polymorphism. This was our first study, and in this study, we included patients from 350 microns onwards. But since then, now we're doing thinner corneas as well. We start off with corneas as thin as 320 microns also. But again, we'll come to some of the other newer studies, and we'll see that maybe it's possible to do even thinner corneas. CACXL, I'm happy to say, has also become a technique that is now, become very popular around the world. These are just some other papers. Francis Price, who's doing it, John Canlopoulos. There's been a study by Brad Randleman, the editor of GRS, on the effect on Brown microscopy used to study the effect of CACXL. Mimoni et al., again in Journal of Refractive Surgery, on accelerated CACXL and their experience with it. We've had a couple of studies from India, other centers, not ours, very respected centers, academic centers who now published their results with contact lens assisted collagen cross-linking, and they've used compared dextran based riboflavin versus HPMC based riboflavin and published their results with that. And of course, we've also had a study together with Farhad Hafezi on thin cornea cross-linking with CACXL. So this was a study with Hafezi and Kling, which actually showed that thin corneas have higher oxygen availability, and so actually the cross-linking that you get with thinner corneas may be better or more effective than thicker corneas. And this is also a study, very interesting study by Farhad Hafezi, which shows the comparison of the stiffening that you get with murine versus lapine versus porcine corneas. Porcine corneas are the thickest, and murine are the thinnest. And you see here that with the same protocol, murine corneas actually stiffen much more than porcine corneas, and that's possibly also translatable to thin corneas, thin keratoconate corneas, that the amount of cross-linking you get with the same protocol, maybe amount of stiffening that you get with the same protocol may be more than with thicker corneas. This is a comparison of the other center that I mentioned, which compared dextran with HPMC-based riboflavin, and they found that HPMC gave you a deeper demarcation line than dextran, and that's possibly because HPMC enhances the stromal penetration. It makes riboflavin go down deeper, and since riboflavin is needed for the cross-linking to happen, you can also get deeper cross-linking. HPMC has the added advantage. It's not just the deeper demarcation line, but also the fact that it also does not deturgis the cornea. Dextran can thin out a cornea, and you're already starting out with thin cornea, so dextran does have that disadvantage, which is not there for HPMC. These are again other techniques, other studies of CACXL by Boris Neiser et al. Here's the study of the biomechanical efficacy of CACXL by Wollensak and Sperl, and they showed that actually the importance of the effect of different types of contact lenses, and also the fact that you can actually increase the effect of CACXL by omitting the riboflavin film on the contact lens. These are the studies by Brad Randleman et al. Using Brown microscopy, and they said that they actually came to the conclusion after their study that contact lens assisted CXL, it provides a straightforward option for cross-linking in thin corneas without requiring complicated equipment or precise manipulation, and the safety has been demonstrated recently. So this was their study. I will go through this a little fast. What they've said is that the contact lens, actually, this is their study. This is CXL, and it shows that these are the stiffening before and after CXL. And after CXL, they found that the maximum effect was in the anterior and middle cornea, not much effect for the posterior cornea. And they found similar effects, results post CXL, where they found significant increase in the stiffening in the anterior and middle cornea, and similar to cross-linking, conventional cross-linking, not much in the posterior cornea. So we saw similar results, as you can see here, post CXL and post CACXL. And as he said, similar stiffening profiles, but overall a decrease in the stiffening by about 70%, which is what we also said. It corroborated with what we said. CACXL achieving 71% of the stiffening effect of standard CXL was their conclusion. And they also said that the contact lens does not actually shift the entire CXL anteriorly, which means it's not that all the cross-linking happens in the contact lens and nothing in the cornea, but what it does is basically blunt the effect of the cross-linking, which also corroborated with what we had said initially. And I'm happy to say that now there's this machine which has incorporated also the CACXL protocol into their machine, Appasamy Associates, and they actually guide you step by step through the procedure, which means you enter the thinnest cornea, and then the machine tells you what to do next. So with that, I'll come to the end of my presentation. Thank you so much.